Right. So just to give you a word of warning, I don't have any typed up lecture notes for today. The first thing that I will do is going to be a table of that combines all of the concepts we've covered. So you're welcome to copy that down, but I do encourage you to go through the process of just making something like that on your own from your own memory at some stage next week. It doesn't have to look the same as mine, because what I will be presenting is how it fits together in my head, but maybe the concepts will fit together differently in your head, and that's fine. But it's useful to go through the process of just putting everything together like that. Then after that, I'm going to give you my personal opinion on a few things, so it's probably better for those things not to be on paper either. And then for the rest of the lecture, I will cover some stuff related to quantum information, and I don't have written notes for that, but I will give you references to Nielsen and Chuang where he covers this stuff in a similar way to what I'm covering. So you'll still have access to typed up notes on what I'll be talking about, even if they're not my notes. All right, so over the last few days, we've been talking about preparations, transformations, and measurements, and we looked at three different aspects of that. We first started off with the ideal case, and then we saw how we could generalize that in terms of statistical mixtures of ideal operations. And then we went the other way and looked at how we could realize realistic operations as operations that are acting on the reduced Hilbert space of some ideal operation in the larger Hilbert space. So let's just kind of go through everything and write down the key concepts. So in the ideal case for preparations, we had a very simple postulate that just said our states are given by vectors in a Hilbert space, and in order to get rid of this physically irrelevant phase, we simply expressed the state as a density operator that was the outer product of this pure state, of this state vector in the Hilbert space. Then for preparations, in terms of statistical mixtures, we said that we could prepare the state psi I with probability pi. So then the density operator corresponding to that would be a convex sum over the density operators for psi I and weighted by the probability pi. And then for the realistic preparations as reduced states of density, of pure states in a larger dimensional Hilbert space, we imagined preparing some bipartite state, psi AB. So let's kind of draw something like a quantum circuit where this is system B, system A. And then we imagined just throwing away system B and calculating the reduced density operator for system A. And then we saw that that was given by rho A is the partial trace over B over the pure state on the bipartite Hilbert space, or composite Hilbert space, like that. Then for transformations, in the ideal case, we saw that I could write down a transformed state, which I'll describe by rho prime, as a state that evolved unitarily according to the unitary operator U. Then in the case of the probabilistic statistical mixtures or probabilistic mixtures, we said something like, I can apply the unitary operator UK with probability PK, And then I would have a rho prime, which was a probabilistic mixture of these UKs weighted by PKs, and I could write it in terms of these operators called Krauss operators. Where the Krauss operators were proportional to the unitary operators. And in this case, I had these conditions on the Krauss operators that A dagger A summed over all K was equal to A dagger summed over all K, which was all equal to the identity. And so this condition here was the trace preserving condition, and this condition here just told us that we had a unital map. That meant it's a map that cannot increase the purity of the state. And then in the case of doing ideal transformations on a larger dimensional Hilbert space, we said, well, let's bring in some sort of, let's imagine our system A and bring in some sort of ancillary system B. Then let's apply a unitary transformation on UAB. And then just throw away system B. And we would have an expression for rho A prime. And then again, we could decompose, or we could write down rho A prime as in terms of these Krauss operators. But now the Krauss operators, rather than being written in terms of unitaries that are applied probabilistically, they're written in terms of this big unitary on the larger dimensional Hilbert space and this ancilla state. So AK equals this operator on A, which comes from sandwiching this operator on systems A, B between Ketz and Braz for system B. And in this case, we still satisfied the trace preserving condition. Same as we did here, but we didn't necessarily have to satisfy this unitality condition. So with these operations, it was actually possible to increase the purity of our state. And an example of that was if we had our two-level atom coupled to the radiation field, then it could spontaneously emit, and spontaneous emission always took the atom to the ground state, which was a pure state. So regardless of where you started on the Bloch sphere, even if you were mixed, in the end, you would end up in a pure state corresponding to the ground state. Okay, and then finally, in the ideal case of measurement, we said that measurements were described by a set of projection operators, PM, where because they're projectors, they satisfy this property of idempotence, that they're equal to their own square. And we could compute the probability of getting outcome associated with the projector M by computing the Born rule, which was the trace of the product of the projector and the density operator. Then for statistical mixtures, we were able to motivate generalized measurements as applying the projector, the set of projectors So the set is parameterized by this I, and the J parameterizes the different projectors in the set. Maybe I could put this. Well, I want to keep the I there. So apply this set of projectors with probability pi. So then I could define a new set of operators, which were these POVM elements. And the notation is a little bit confusing. I'm not sure what's the best way to write it, but I'll do it like this. So here, M is a label that represents both I and J. And then you can construct a big set of operators, EM, by multiplying the projectors by the probability of making the measurement that corresponds to this set of projectors. And so then we could also compute something like the Born rule. So a generalized Born rule that says with probability, the probability of getting outcome M is given by the trace of now the POVM element times the density operator. Okay, and then for generalized measurements that were done as projective measurements on a larger dimensional Hilbert space, we motivated it by saying we have the system rho A that we're trying to measure, and we introduce this ancillary system phi B. Now, we want to make a projective measurement on this entire system, but we can always decompose a projective measurement on the entire system into some unitary on both systems, and then a projective measurement just on the ancilla system. So then again, we can describe our measurements with a set of operators EM. Where EM can be decomposed, so these are POVM elements, and they can be decomposed into these other operators called measurement operators, where the measurement operator is defined in terms of this unitary that we applied and the ancilla state that we prepared. And then again, we can compute the probability of getting outcome M by something like the Born rule. In terms of the POVM element and the density operator rho. So then for the measurements, we also had some state update rules, but I won't write them down here. But when you go through the process of piecing it all together, I encourage you to also see how the state update rules fit into this whole picture. So you can see that there's some similarities between these two pictures. Mathematically, the descriptions are going to be the same, but then how we interpret these operators is going to be somewhat different. And what we've been able to do here is more general. So we can do more general operations by coupling to some other system than we could do in the case of probabilistic mixtures. So that's the case for transformations and measurements. But actually, what we saw yesterday for preparations was that the case of having a reduced density operator of an entangled state is indistinguishable from a reduced density operator, from a density operator created as a probabilistic mixture of pure states. So as long as you have the same density operator, you can't distinguish between these two things. And actually, yeah, so as long as you have the same AKs, in this case, then you wouldn't be able to distinguish between how you implemented those AKs. And if you had the same EMs here, you wouldn't be able to distinguish between how you implemented them. But there are situations where here you can do more general things than what you can do here. Okay, and so kind of between here and here, there's this notion of entanglement. So that's intimately connected because we can, in order to get the generalized case from the pure, from the ideal case, we need to introduce this idea of entanglement and then with another system and then throwing away that system. And so you can, I think what's interesting is to kind of think about how you get the limiting cases. So in some sense, this is a limiting case of that. And it's useful to think about how this relates to this as well, like whether the limiting case goes in one direction or the other direction. Okay, so are there any questions about how all that fits together? So I think this is a really nice way of looking at things. The framework that I presented here, it's really useful both from a conceptual perspective as well as a practical perspective. So seeing how all of the different aspects of the theory fit together, the preparations, transformations, and measurements, it kind of lets you have this scaffolding in your head that you can use then to kind of try and fit different ideas into. It's a nice lens to look at different problems, nice lens through which to look at different problems. And it also, it gives you practical tools that you can use to solve complicated problems. So often modeling how systems interact with environments can be really difficult if you're trying to model the entire system. But if you can have some effective description on the reduced state, then that can be really useful. And so this framework has been really, really powerful in the areas of quantum information and quantum foundations, but it's not really a framework that's used in other areas of physics that are typically not areas related to quantum theory, but now is starting to kind of like bleed into looking at quantum aspects related to the other areas of physics. And I really think you as the next generation, I think it's a good idea to try and see how you can make connections between this type of like the modern approach to quantum theory to see how that connects to the other areas of physics. So I kind of wanted to highlight some areas where I think this connection would be really useful, or kind of has started to be really useful. If you kind of take a naive undergraduate quantum mechanics approach to like looking at quantum systems, then maybe you might miss some interesting physics that you wouldn't miss if you looked at it through, if you treated measurement, you know, the way that it's supposed to be treated, and you treated preparations the way they're supposed to be treated. So one place where I think it would be really interesting is in the case of particle detection. So there are detectors like the LHC, or maybe even something more basic like a bubble chamber, which is like some sort of compressed liquid, and they, you know, you measure a quantum particle and watch its path. It like makes some sort of path and spins around. And so those measurements are treated classically. You know, you're watching some sort of particle move and you're measuring its position and momentum at the same time. And you know, I know like in the LHC at the moment, the technological bottleneck isn't that they're not treating the measurements quantum mechanically. There are like much bigger problems. But I think from a fundamental perspective, it would be really interesting to have a full quantum theory of quantum measurement theory of particle detection, because these are quantum particles that we're detecting, and yet we're treating it classically. So fundamentally, I think it's interesting. But then maybe sometime in the future, the experiments are going to get so good that we will need to have a full quantum theory. Also in astrophysics, not in terms of measurement, but in terms of preparations, I know there are astrophysicists that are starting to think about quantum light rather than the quantum nature of light. So they think about what happens to single photons in space when they interact with like the quantum lens or something. And the way that typically they treat single photons is to assume that they have a classical field, and then that it's just like really, really weak, that I have, on average, a single photon. And we know that weak coherent states have very different properties to single photon states. And so I think you need to be a little bit more careful about how you treat the preparations and treat them properly quantum mechanically, rather than just, saying that I have only a few photons in my classical field. So I think there's, this type of framework has a lot to add to those areas as well. And maybe there'll be some interesting physics that you would miss if you didn't do it this way. And I think it can also help you from a practical perspective. I know some people who, like in the area of cosmology, are studying things like entangled pairs being created. I've mentioned this before. Entangled pairs being created at event horizons of black holes, and they're worried about things like entanglement. And because they're very, very smart people, and they are excellent at what they're doing. But maybe if they're not familiar with these techniques that exist in quantum theory or quantum information, they spend weeks trying to do things from first principles, where if they knew these techniques, they could do something like in half an hour that I know that they've been spending weeks on doing. And so it's nice to spend weeks on figuring something out yourself, but at the same time, the older you get, the less time you have, and it's really good to have a bunch of efficient tricks under your belt. So even if you're not going into the area of quantum information, I think knowing these types of things will make you a useful collaborator to have when you're working with people who are working at the intersections of different disciplines. I think also these techniques would be useful in condensed matter, where they're starting to look at things like phase transitions, but trying to understand them from a quantum mechanical perspective. So those things are phenomena that happen from having many different particles interacting with each other in certain ways. And so as we saw in the tutorials, that different ensembles can seem different depending on whether you're just measuring one particle from the ensemble or treating the whole thing together. So knowing how all of that fits together will make you capable of choosing which approximations to make to get the physics that you want, but still be able to compute things efficiently. So I think this sort of thing will be useful in condensed matter. In areas like quantum thermodynamics, I think it'll be useful both from a conceptual perspective, but also from a computational perspective. So some questions that arise in quantum thermodynamics is, how can we get thermalization if everything behaves unitarily? So thermalization should, take some sort of pure state, and then if I have, a pure state in some isolated box, and then eventually it's going to thermalize, how does that happen if everything involves unitarily? So some ideas are, well, maybe the whole thing is pure, but if I just look at some subsection of the system, it seems mixed and it seems like it's thermalized. So I think these techniques will also be useful in studies, in trying to understand thermodynamics from a quantum perspective. So that's kind of like my spiel for motivating you to take this stuff seriously, even if you're not actually interested in pursuing quantum information and quantum foundations, because I think these techniques will become useful in those other areas as well. All right, so is that a wave or no? Okay, no questions. Okay, so that's pretty much it for the operational stuff and the generalized postulates. And now I just want to go through a few fun things, fun topics from quantum information. So I want to say a little bit about the no cloning theorem, which someone brought up at some stage. And I want to then tell you a few things you would need to know for me to be able to explain the quantum teleportation protocol. How many of you have seen the quantum teleportation protocol in detail? All right, 2 maybe waves. Amazing. This is like very exciting for me then, because it's cool. Okay, so what would you guess that the no cloning theorem tells you? Based on the names. You can't clone? No clones allowed. Okay. And it's a quantum theory course.
You can't copy quantum clones without
No quantum clones are allowed. Yeah, yeah. You can't copy a quantum
state without changing the original one.
Without changing the original one. Actually, well, so that is not what the no cloning theorem says, but that is what we're going to see later in quantum teleportation. So it is related to that. Okay, so no cloning theorem says that it's not possible to copy an arbitrary unknown quantum state. So if it was an arbitrary known quantum state, then you could just prepare that known quantum state. But if you don't know what it is and it's arbitrary, then you can't make a copy of it.
It's not really quantum if you don't know what something is.
So let me just write that down.
If you don't know what something is, how are you going to copy it?
So this might not seem so weird at first, but it is kind of weird when you think about it from an information perspective. So in classical information theory, if you have some string of bits, you can always copy it. You don't have to know what it is. You can, copy. You've got some digital representation of your photo. You can just like go Control-C, Control-V, and like copy it on your computer. Now you have 2 copies, identical copies of some string of bits. And the process of doing that doesn't require you to know in the first place what that string of bits was. While if you have a quantum state, there's no device that you can build that is going to be able to copy that quantum information onto another system. So I have kind of 2, the proofs are really short, so I'm going to give you 2 different ones because the first one is like slightly less general, but I think it's more conceptually clear what's going on. And then the second proof is more general. So I'll call the first thing an intuition, although it is, people do use it as a proof of intuition. Although, I mean, okay, whatever. I'm a physicist, so I don't have to like worry too much about what proof really means. Okay, so how do we do this? So let's consider that we have a process that clones the basis elements 0 and 1. So the way that this would work is I would have my state 0, and then I want to copy it onto some physical system. So maybe like this was an analogy to a photocopier. I would have like some blank piece of paper onto which I'm going to copy this information. So I'm going to introduce some other system prepared in the blank state. And then I want to have some sort of unitary operation on both of those systems that then copies the information onto system B. So I can do that. I can build something that does this. And I can also build one that does this. And if you stare at this for like long enough, you'll be able to even just write down what that unitary operation would be. That would do something like that. But let's assume that I have something like that. So what would happen now if I tried to copy an arbitrary superposition of 0 and 1? So if I have, okay, so now I want to copy the state psi, which is equal to alpha 0 plus beta 1. So if alpha and beta are complex numbers, then this is some arbitrary pure state. So if I apply UAB to the state psi, tensor product with my blank piece of paper, then I would get alpha UAB 0 blank plus beta UAB unitary on 1 blank. So the reason I write that is just due to the linearity of quantum mechanics. And then I would get something that looks like that. And that is not what we would expect if we actually successfully copied psi onto the blank piece of paper. Because if we had done that, we would have had something that was a tensor product of these two things, and I would have 4 terms. So what does this tell us? That you cannot have a unitary that clones an arbitrary unknown state. Okay, so I like that proof because it's kind of clear what's going on. But some people don't like it because you have to pick some specific bases in order to do it. So there's another way of doing it where you don't have to specify a basis. So again, let's imagine that we have a U that clones some arbitrary state phi. so it takes phi and some blank piece of paper and then copies that phi onto B. So now I can compute. Now consider that I have two arbitrary states. And for the purposes of the proof, I'm just going to compute the inner product between these. And the inner product between the blank pieces of paper. So I can rewrite this as an inner product between the inputs to the cloning device like that. And then given this definition, I can rewrite that. Oh yeah. So I can say that phi A blank is equal to the inverse of the unitary. So I can replace those terms in the inner product with this. And now because these things are unitaries, they become the identity, and I get that is not right. Okay, and because blank is taken to be some sort of pure input state, then the inner product of that and itself is going to be equal to just that. So I'll write it on that side. So what we've shown is that if there was a U that could clone this state, this would have to be true. And this can only be true in two situations, either when this inner product is 0 or when this inner product is 1. So again, this tells us that if such a device existed, all it could do is clone either two states that are the same or two states that are orthogonal. But in this proof, phi and psi was supposed to be arbitrary states. And so this tells us that we cannot have a U that can clone arbitrary states. So I think this line of reasoning takes a little bit more time to process, and you kind of need to sit for 5 minutes and think about it. But it does, in the end, like fall together. But I find this first proof to be a bit more intuitive. So this by itself is a interesting result, but it kind of becomes a little more interesting in the context of quantum teleportation, which we'll see in a minute. Okay, so now I'm just going to tell you a few little things that will be useful to know for the teleportation protocol. One of them is this idea of the 4 Bell states. So you saw already one of the Bell states in your tutorial yesterday. It was called a Bell pair, but that's just another word for a pair of qubits prepared in the Bell state. So the one you saw was the phi plus state, which was up, up, plus down, down. So all 4 of those states are maximally entangled states. All 4 of those states, if you looked at just one of the systems and took the reduced density operator, it would be a maximally mixed state. And also these 4 states, they form a basis for the space of 2 qubits. So you can actually use them to construct a projective measurement. That's a 4-outcome projective measurement. And that's the type of measurement that we're going to use for the teleportation protocol. To do the calculation, it'll also be useful for us to rewrite these terms in terms of the Bell states. I'll just do that. And actually, maybe just to emphasize that this is really a state of 2 qubits, I'll label these things. Okay, so this seems like a kind of strange measurement to make, a measurement in this entangled basis. How would you do that physically? How do I make a device that measures some entangled state? Seems kind of strange. And so typically the way that one would construct that is by first doing a unitary operation to entangle the states, and then just doing a regular projective measurement on the local qubits or on the individual qubits. So the particular set of operations that you would need to do specifically that measurement. So imagine I have system A and system B coming in, and then I have some device that does the Bell basis measurement. that's equivalent to having two states come in, doing something called a controlled NOT operation, which I will define in a moment, and then applying something called a Hadamard gate. So that's just a unitary operation on one qubit, and then doing regular two-outcome projective measurements. Where here M can have outcome 0 or 1, and here N can have outcome 0 or 1. So that's called control NOT. And so what the control NOT does is if system A is prepared in the 0 state, then it just applies the identity to the B system. And if system A is prepared in the 1 state, then it applies a sigma X operation. So it takes a 0 to a 1 or a 1 to a 0, which is the logical NOT operation, which is where this terminology comes from. And then the Hadamard operation, it's a single qubit operation that takes the 0 state into the plus state and takes the 1 state into the minus state. So you can go through and show that the combination of 4 separable measurements corresponding to these projectors on each of these qubits actually is equivalent to making the Bell state measurement. So I will go through and just show it for one of the measurement operators, and then I will just tell you what the results are for the other 3. But you can convince yourself that it's true. Actually. Okay, and yeah, just so we're a little bit more clear. So the projectors corresponding to the 4 outcomes here, I will call them B00, B01, and the 4 outcomes corresponding to these measurements, I will call them E00, and so what we want to show is that by applying those operations onto this projector, we're going to get this projector. And because they're projectors, we don't actually have to show it for both the bra and the ket. We can just show it for the ket and extrapolate from that. So I want to show that C0 and Hadamard and local projectors give spell basis measurement. So for example, for the first one, I want to show that I can go from 0, 0 to the first spell state by applying those operations. So let's start. So first I have the state 0, 0. I then want to apply the Hadamard operation on the first qubit and do nothing to the second qubit. And then I want to apply the C0 operation on A and B. So, okay. So we know that the identity is going to do nothing to that state, and the Hadamard will take the 0 state to the plus state. So we get plus 0, and then the C0 acting on them. Where then I've just rewritten the plus state in the 0, 1 basis. And now we know that the C0 will do nothing. If the first qubit is 0, it'll do nothing to the second qubit. And if the first qubit is 1, it'll flip the second qubit. And so we end up with 0, 0 plus 1, 1. Which is equal to the 5 plus state. And so you can go through and show that there is a relationship between each of these projectors and those projectors as long as you just repeat the process of applying the Hadamard on the first qubit and then the C0 on the other qubit.
Let's check for in the bell states, should the last two be swapped?
In the
The bell measurements. Yeah.
should that one
Should be 1, 0, be 1, 1.
okay.
It just seems like
Yeah. Yeah.
No, not the bell ones, not the no.
You want that to be plus? Sorry, I'm just not sure what you want me to change.
The types of 5s should be and B10 and B11, the types of 5s should be the other way around, I think.
You think? Okay, can we, I don't know if I can do it on the spot, but let's see.
Just from how
Yeah.
you define the bell states over here.
Yeah. I'll trust you guys.
I don't.
Yeah. Yeah, I just find it impossible to do it while I'm up here. But yeah. Let's go with that. And you can all check yourselves anyway.
One more question is, should the Hadamard be before the C0?
You're saying that because of the way that I was doing these operations? So no, because I'm not applying. If I was thinking of this as a state, then my my circuit would be kind of reversed, and I would have like the state 0, 0, then the Hadamard, then the C0 gate. But because here I'm changing the basis of the measurement rather than the state, I go in the other direction. So I first define the measurement operator, then I apply the Hadamard, and then I apply the C0. So when we want to change the measurement basis, we apply the inverse unitary operation to the state. Okay, so I think we have everything that we need. So we need to know how to make a Bell state. We need to know how to make a Bell state measurement. And I think that's it. Okay, so here is the teleportation story. As always, it starts with Alice and Bob. And they used to hang out at some stage. And when they used to hang out, they had a lot of foresight and they prepared a Bell state. And then I guess maybe Bob was an astronaut or something, like he needed to go to work and he got on a spaceship and like went to the moon, I don't know. And he decided to take one of his Bell states, one of the qubits corresponding to his, the qubit corresponding to his half of the Bell state he took with him, and Alice kept the other one. So we start with Alice and, oh, let's do it again. Alice and Bob sharing a Bell pair. And then Bob goes really far away. And then we have Alice and Bob sharing the Bell pair, but, you know, they're no longer next to each other. So maybe Bob is on the moon or something. And now it turns out that Alice really, for whatever reason, wants to send an unknown quantum state to Bob. So she has another state. So maybe let's call this A2 and call this A1. Label this A2. So the state describing the joint pair between Alice and Bob, that still stays the same, but then we also have another state for Alice, maybe labeled by A1. And Alice and Bob don't share a quantum channel, which means that they don't have any means of sending a quantum state directly between each other. So she can't just, send a photon encoded with this information to Bob, or maybe she has it in some physical system that she can't send. She does have a classical channel, but in order to be able to transmit, well, if she knew what that state was, then she could, in principle, transmit the classical information that to Bob that he would then use to prepare that state. But that would require an infinite number of bits because an arbitrary quantum state is described by continuous complex numbers. But also in this case, we're imagining that she doesn't know what that state is. So she has some unknown state and she needs to send that to Bob. And she can't measure it because if she measured it, she'd just project it onto some basis and collapse it. And she'd just get an outcome 0 or 1, but she wouldn't really know what these alphas and betas were because she only has one copy of this state. Okay, so that's the scenario. And so the way that this happens is that, well, the way that Alice manages to send her unknown state to Bob is by making a joint measurement on her pair of qubits using this Bell state measurement. So it's an entangling measurement. And then when she implements this measurement, she will get one of 4 outcomes. And then she will communicate her outcome to Bob using a classical information channel. So she requires 2 bits of information to tell whether it's 0, 0, 0, 1, 1, 0, or 1, 1. And then she communicates that to Bob. And then depending on the outcome of her measurement and the message that Bob receives, Bob has to then apply a unitary transformation to his state. And after all of that, we end up with Bob's qubit being prepared in the state that corresponded to Alice's initial qubit. So we'll go through step by step and see how that happens. So it's easiest to see everything that I just described. It's easiest to see that as a quantum circuit. So I can draw it by first saying that Alice, well, I'll put Alice and Bob's shared qubit on this rail, well, these two rails, and then Alice's arbitrary qubit on this rail. And then, so let's call this A1, A2, and B. And then I will apply the Bell measurement here. Okay, so let's first just start by writing down the input state. So we have psi A1 and the Bell pair, which is shared between Alice and Bob. And then I can expand that out. Alice1, Alice1. And I will expand it out just a little more. So I am keeping an implicit ordering that I've got Alice1, Alice2, and Bob, just to save myself writing out the labels in every step. But I will label it when I think it, when I'm trying to emphasize a point. But here I've just expanded everything out. And now, because we know that Alice wants to make this Bell state measurement, it would be really useful if we could rewrite just Alice's qubits in terms of the Bell states. So what I can do is replace each of these 0, 0, 0, 1, 1, 0, and 1, 1 with these useful expressions that I computed just before. So replace the basis states in terms of the Bell states up there. Okay, here just the label A means that both of the qubits correspond to Alice's two states. And now what I will do is just rearrange the terms a little bit so that we have 4 terms that correspond to the 4 outcomes of the Bell measurements. Okay, now it should be kind of clear what's going to happen. So Alice will measure in the basis corresponding to these 4 states, and she will get an outcome. There's a 1/4 chance, 1/4 probability that she'll get, or maybe actually, no, it should be 1/4 probability that she'll get each outcome. And when she gets a specific outcome, she's going to collapse the entire entangled state to just one of these 4 terms. So if she gets the outcome corresponding to this state, then she collapses Bob's state to that state, which is great. So now Bob's state is going to be the state that Alice started off with. If Alice gets this state, then Bob's qubit will be collapsed to that state, which is almost right, but not quite. If Alice gets this outcome, Bob's qubit will be collapsed to this state, and if Alice gets this outcome, Bob's qubit will be collapsed to that state. So simply Alice making a measurement doesn't actually help Bob very much, because even if Bob knows that Alice made the measurement, he doesn't know what her outcome was. So his representation of the qubit is going to be a statistical mixture of all of these 4 states. So he doesn't, at that stage, like as far as he's concerned, it's a maximally mixed state. But then when Alice communicates what the outcome of her measurement was, then he knows, oh, in fact, I have this one. And now if I want to recover Alice's original state, I know I just have to apply some unitary operation. So in this case, the operation that he has to apply is the sigma z operation, because the sigma z operation takes a -1 to a +1. It always puts a minus sign in front of the 1 state. In this case, if Alice communicates that she got that outcome, he has to apply the sigma x operation, which is the bit flip. So it takes a 1 to a 0 and a 0 to a 1. And then in this last case, he has to flip the bits, and then he has to put a minus sign in front of what becomes the 1. So he applies a product of sigma x and then sigma z. So we can actually draw this on the quantum circuit. So we can say that we now have some outputs of the measurement, which are m equals 0, 1, or n equals 0, 1. And typically in the quantum circuit drawings, when people draw double lines, that means that it's a classical channel as opposed to a quantum channel. So then there's some sort of classical output that goes to here, and then we apply a unitary operation that depends on these outputs. So it's sigma x, sigma z to the power of N, M. And then what comes out is alpha plus beta 1. So you can see if M and N are 0, then this is just the identity because, well, operator to 0 will be 0, well, will be the identity. So nothing's going to happen when this is 0, 0. And then when you have the other combinations, you'll apply either a sigma X, sigma Z, or a product of the two. So that's kind of neat, I think. I have a few observations to leave you with, which maybe you can think about if you like. One of them, are we violating the no cloning theorem here?
Distracting. You're distracting the original one?
Yeah, exactly. So even though we were able to copy an arbitrary state from Alice's to Bob's system, we destroyed the original system because after making the measurement, regardless of what the outcome was for Alice, the original qubit is going to be left in the maximally mixed state. So she will have no longer any information about what alpha and beta, or no access to figuring out what alpha and beta were. Okay, so initially I said that an arbitrary quantum state would require an infinite number of bits to specify. So it's kind of interesting that even though an arbitrary quantum state takes an infinite number of bits to specify, you can only ever use it to send one bit of information. Because when you send your quantum state, the person then can only just make a measurement that collapses it to a 0 or a 1. So you can't use it to send an infinite amount of information, but it requires that much information to specify it. And now here, what we've done is we sent a state that requires an infinite number of bits to specify, but we were able to send it just by sending 2 classical bits and using a resource, a resource that is shared entanglement. So I don't have anything specific to say about that, except that it's interesting trying to make connections between what type of resources allow you to do what type of things. Another closely related thing to this is something called superdense coding, which is this idea that you can, if you share a Bell pair, so if you have entanglement, then you can actually communicate 2 bits of information just by sending 1 bit. And that's something that's closely related to this. But we can talk a little bit about that if you like later this afternoon. What else? Okay, yeah, so we're not cloning the state because we destroyed it. And then the other thing that I think is just kind of like weird to think about. I mean, ultimately it makes sense if you think about the whole system, but I think it's interesting to ponder is that at this point, Bob's qubit obviously is in the maximally mixed state because it's just the reduced density operator of the maximally entangled state. So here so we're assuming time is going that way. So here it's maximally mixed. Then here Alice makes her measurement, which projects out one of these states. But still, as far as Bob is concerned, his state at this point is still arbitrarily mixed, except now it's a mixture of one of these 4 states, rather than being like, even if Bob knows what the measurement outcome is, it's like you can think about it as a statistical mixture of those 4 states rather than being the reduced density operator of this entangled state. And then what's kind of weird is when he gets that information from Alice and applies a unitary operation to his mixed state, it becomes a pure state. But we know that by applying unitary operations, we can't take a mixed state to a pure state. So something here is going on that's like somehow related to how much knowledge Bob has about the system. Like his description of the state just changes from like Alice sending him a message and saying, hey, this is the result I got. So, I mean, maybe you can think about that as like Bob making the measurement on his qubit or not. I mean, there's like loads of different ways of thinking about it. But I think it's just something interesting to ponder in your spare time. So that's all I wanted to say about the quantum information stuff. I gave you my spiel about how the generalized framework is useful. And I was hoping to have more time for a Q&A session, but it looks like we're almost finished. So maybe I'll just wrap it up now. And if you guys have some questions after the class, you can come chat with me, and then we can continue discussion in the tutorial. And just to tell you, in the tutorial, we're going to start again at 3:30, so right after David's class, and then we'll have a 15-minute break for Friday social at 4 o'clock. And in the first half an hour, we're going to have a group exercise where you guys are going to pair up and answer interview questions for each other. So we'll give you a set of interview questions. And the idea will be that you won't be able to look at your lecture notes. You'll have to practice answering those questions off the top of your head. It'll be painful, but it'll be good for you. So that'll be the first half. And this will be on the material I covered as well as the material Meta covered. So she's going to be there for the first half an hour. And then when you come back, I've got some extra problem sets for you to work on. So I'll see you, at 3:30.